So hello everyone, my name is Kunal Tyagi and I am from section G, and today I'll be explaining about the Intel Xeon Phi processor family, which is Intel's many core architecture designed specifically for high performance and computing workloads. The Xeon Phi series, including Knight's Corner and Knight's Landing, represents Intel's approach to provide massive parallelism using a highly scalable architecture. Unlike a traditional CPU that typically offers anywhere from 4 to 32 high performance cores, Xeon Phi provides 60 or more streamlined x86 cores, each capable of running multiple threads and wide vector instructions simultaneously. The goal of this architecture is simple: maximize throughput, which is the total amount of work completed per unit time. Unlike GPUs, which rely on specialized instructions and complex memory hierarchies, Xeon Phi maintains x86 compatibility, making it easier for developers to port existing code. So throughout this talk, I'll walk you through the architectural layout, memory hierarchy, execution model, programming environments like OpenMP and MPI, and later we'll be looking at how algorithms will be implemented in this processor. So coming to the next slide, which is basically about this introduction to the Xeon Phi processor. So uh, we take a closer look at the architectural characteristics that define Xeon Phi. So at its core, Xeon Phi is built around a many core philosophy, meaning it opts for large quantities of simpler cores rather than a smaller number of high performance ones. So each Xeon Phi core contains a robust 512 vector unit, also known as a VPU, which is capable of performing a 16 double precision floating point operations per cycle. This wide SIMD capability is central to the processor's computational power. The architecture encourages developers to restructure their algorithms so that parallelism exists at both the thread level and the vector level. Another important concept is the execution model. Xeon-Phi cores support up to 4 hardware threads, allowing the processor to hide a latency by constantly switching to the threads that are ready to run. This is similar to in spirit to GPU warps and wavefront execution, but remains more flexible because the architecture continues to follow x86 conventions. So Xeon-Phi design makes it exceptionally well suited for workloads like scientific simulations, sparse metric operations, AI workloads, large-scale numerical modeling, and weather forecasting, especially anything requiring large amounts of parallel computation. So overall, this architecture aims to combine the aspects of CPU and GPUs, bridging the gap with a unique balance of programmability and high throughput. Then up to the next slide, which is about the Xeon-Phi development environment. So in order to efficiently develop Xeon-Phi, we need the right development environment and the tool chain. So Intel provides the One API toolkit, previously known as the Intel Parallel Studio, which includes advanced compilers, libraries, analyzers, and debuggers. So one major advantage of Xeon-Phi is that the programming model is flexible. So we can basically write the applications using familiar paradigms like OpenMP, MPI, or the OpenCL, while benefiting from vectorization optimizations automatically applied by the Intel compiler. There are mainly two modes of execution here: offload mode and the host and the native mode. And in the offload mode, the host CPU in a typical system controls the Xeon-Phi card and can offload specific compute intensive sections. While the native mode, on the other hand, treats the Xeon-Phi as its own standalone computer with its own Linux-based operating system. So this is particularly useful in HPC clusters where thousands of Xeon-Phi cards may each run their own processes in parallel. So here the key point is that Xeon-Phi was designed to make the transition from CPU programming smooth, enabling developers to use familiar tools and languages. So the next is the data movement in Xeon-Phi architecture, which will basically is about the most crucial aspect for achieving high performance on Xeon-Phi. So even if the compute performance is extremely high, inefficient data movement can become the limiting factor. So each core of the Xeon-Phi includes its own L1 and L2 caches, and all the L2 caches are kept coherent through a mesh interconnect. So this design is ensuring that the data consistency is maintained even across 60 or more cores. So then we have the high bandwidth MCDRAM, a highly innovative part of Knight's Landing. MCDRAM provides up to 60 GB of very high speed memory with bandwidth significantly exceeding traditional DDR memory. So with three different modes, flat, cache, and hybrid, developers can choose whether MCDRAM acts as addressable memory or as a cache layer. So the flexibility is invaluable for tuning performance, especially in memory bandwidth. Intensive workloads like vector operations, streaming algorithms, and stencil computations are there. So then next is about the vector arithmetic and parallel execution, wherein the Xeon-Phi's biggest computational strength lies in the vector arithmetic, and this slide highlights exactly why that is. Each core is equipped with a 512-bit SIMD vector unit capable of operating on 8 double precision or 16 single precision numbers simultaneously. However, vectorization is not automatic. Developers often need to restructure loops to help the processor to the compiler to understand how to parallelize operations. So Intel compiler provides vectorization reports that tell whether a loop was successfully vectorized, partially vectorized, or could not be vectorized at all, and why. So in addition to vectorization, hardware multithreading plays a major role here. So Intel Xeon Phi, it offers up to 4 hardware threads per core, and this means a 72 core processor can expose nearly 300 concurrent threads, each helping to hide latency and keep the exhaustion execution in units busy. So then we come on to the next slide, which is about the control flow and parallel work distribution. So the control flow and parallel work distribution slide basically represents about the distributing work effectively across hundreds of threads. OpenMP is often the go-to parallelization method because it makes it easy to split loops across many threads. So for distributed computing environments, especially the HPC clusters, MPI is commonly used in combination with OpenMP. Each node may have multiple Xeon-Phi cards, and MPI coordinates communication between nodes, while OpenMP handles parallelism within each card. So thread affinity is another powerful performance tool. So by controlling how threads are assigned to core developers can reduce NUMA induced latency and improve the data reuse. So overall, the key to the performance is understanding both computation and communication and how they are interacting at scale. The next slide is basically about the implementation of the algorithms on Xeon-Phi. So when designing algorithms for Xeon-Phi, three key optimization strategies consistently appear: vectorization, threading, and memory access. So first of all, the vectorization part where the algorithms must be structured so that operations can be applied uniformly across the data. This often requires removing dependencies within loops, aligning memory, and ensuring that the data is contiguous. The next is the threading. The many core architecture demands heavy parallelism. Using OpenMP parallel for loops is critical, but equally important in minimizing the synchronization between the threads. So the next is the memory optimization, wherein the proper alignment, stride one accesses, and caching behaviors have enormous impact on the throughput. So in many cases, the limiting factor isn't raw compute but memory stalls. So by optimizing the memory access using MCDRAM effectively and minimizing the caches misses, performance can often double. Then we have a code example which basically demonstrates or presents a simple example that demonstrates the combination of OpenMP threading and SIMD vectorization. Uh, so the next slide then represents about the compiling and running Xeon-Phi applications. So compiling for Xeon-Phi involves using ICC or the newer ICX compilers. So these compilers include powerful optimization flags that target the Knight's Landing or Knight's Corner architecture specifically. So here the developers can choose between native execution, where the application runs directly on the Xeon-Phi processor, or offloaded execution, where specific functions run on Xeon-Phi while the main program executes on a host CPU. So the next slide then talks about the conclusion and the future optimization parts. So in short, the Intel Xeon architecture represents an important milestone in the evolution of many core processors. Although Intel discontinued future generations, the lesson learned from this architecture continues to influence today's CPU, GPU, and accelerators. So this was about the presentation part. Now coming to the next part, the part two, which is about the code demonstration. So we'll do that. All right, so we are now in this Ubuntu terminal. So here I have used Gem 5 as my processor, as my simulator for this Intel Xeon processor on the Ubuntu terminal. So here, as we can see, nanofibo.asm is the file. So wherein the Fibonacci numbers will be the code for the assembly code for the Fibonacci numbers is presented. So once we enter, we see this code here. So this is an NASM assembly program which is specifically designed for computing the Fibonacci numbers, for printing the first 10 Fibonacci numbers. So this is the overall assembly code, and it reserves, first of all, it reserves the memory. The dot data section holds a new line character for printing, and the dot BSS section allocates space for 10 Fibonacci numbers and a temporary buffer for converting numbers to ASCII. So then the program begins execution at underscore start, where it initializes the first two Fibonacci numbers, 0 and 1 in memory, and sets a counter R8 to 2. Then a loop calculates the remaining Fibonacci numbers by loading the previous two numbers from memory, adding them together, and then storing the result in the final position. So this increments the counter with each iteration until all the 10 numbers are computed. So once after the computation is done, a second loop iterates through each Fibonacci number, loading it into the RAX and passing it to the int underscore to underscore ASCII subroutine, which converts the integer and a string into a string, which handles the special cases of 0 and for other numbers repeatedly, divides by 10 to extract digits in reverse order and then reverses them in memory to get the correct string representation, which returns the string length in the RBX. So, like this, each ASCII string is printed to the terminal using the Linux write syscall, followed by the printing a new line before the loop moves to the next number. And once all the numbers are printed, the program exits cleanly using the exit syscall. So it exits using the exit syscall. Throughout the program, demonstrates the use of 64-bit registers for memory addressing, arithmetic operation loop, subroutine calls, and direct interaction with the Linux system via syscall, effectively combining computation, memory management, and output in a single step-by-step assembly language. So now we'll be presenting the output. So for that, we first assemble this code. For that, we write a specific command, which is uh, so once we have assembled the code, then we link it using this specific command. So yes, so right. So this is the output. So once we have typed this last command, so it prints the Fibonacci numbers. So just presenting the assembly code once again for explanation. Uh, so right, this is the assembly code that we have basically implemented for the output. So here the NASM assembly program is designed for computing and printing the first and Fibonacci numbers on a 64-bit Linux system. And here the memory, first of all, it reserves the memory. The dot data section here, it basically holds a new line character for printing, and the dot BSS section here is allocating space for 10 Fibonacci numbers and a temporary buffer for converting numbers to ASCII. So the program begins execution at underscore start, which will first obviously initialize the first two Fibonacci numbers in the memory, and it will set the counter R8 to 2. So then a loop will calculate the remaining Fibonacci numbers by loading the previous two numbers from memory, adding them together, and storing them result in the next position. And it will continue to increment the counter each iteration until all the 10 numbers are computed. So after computation, a second loop iterates through each Fibonacci number, loading it to the RAX and passing it to the int underscore to underscore ASCII subroutine, which will convert the integer into a string. And this will handle the special case of 0 and for other numbers repeatedly divides by 10 to extract digits in reverse order and then reverses them in memory to get the correct string representation. Then finally, it will return to the string in the string length in the RBX, and then each ASCII string is printed to the terminal using the Linux write syscall, followed by printing a new line before the loop moves to the next number. And throughout this program demonstrates the use of 64-bit registers for memory addressing, arithmetic operation, loops, and subroutine calls. So like this is how the code looks and this is how it works. So thank you.